Assalamualaikum warahmatullahi wabarakatuh. I'm Fauzi bin Ahmad. Group assignment passive RCL low-pass filter. My lecturer Dr. Khairul Anwar bin Ibrahim. My clique member group Muhammad Amirul, Amin bin Sazali, Muhammad Syamil, Irfan bin Ruslan, Chah Chinyo, and I'm Fauzi bin Ahmad. Group member rule Muhammad Amirul, Amin bin Sazali, leader group, Muhammad Syamil, Irfan bin Ruslan, circuit drawing engineer, Chah Chinyo, test engineer. I am Fauzi bin Ahmad, analysis. Low-pass filter is a circuit that can be used to modify, restructure, or reject any undesirable high-frequency in electrical signal while accepting or passing just the signal that the circuit designed to want. In the one word, they filter out undesired signal with the ideal filter separating and passing sinusoidal input signal based on the frequency. Pass filters are often built with simple RC resistor-capacitor network in the frequency application up to 100 kHz and RCL resistant. Low-pass filter is a circuit that can be used to be modified, restructure, or reject any undesirable high frequency in electrical signal while accepting or passing just the signal that the circuit design want in the world. They fill out undesired signal with ideal filter separate and passing sinusoidal input signal based on the frequency. Passing filter are often built with RC resistor capacitor network in a low frequency application up to 100 kHz and RCL resistor induction capacitor component in higher frequency application. Low pass filter allow signal with frequency lower than a preset cut-off frequency to pass while attenuating signal with frequency higher than the cut-off frequency. The frequency response of the filter determined by design. In the audio application, a filter is known as a high cut filter or treble cut filter. The component of high cut filter is a low filter. The path filter version frequency used prototype filter by filter design. That is, a filter have some bandwidth and impedance as a signal by circling the desired bandwidth. Low pass filter, the low pass filter version, low pass version in frequently used as a prototype filter by filter design. There is a filter have some bandwidth and impedance as the input signal by circling for the desired bandwidth and impedance and translating into desired band from the desired filter can be obtained from the prototype. That is low pass filter and high pass, band pass, or band stop. Second order RCI filter and RCI circuit, the letter R L and C can be in a different sequence. Is an electrical circuit consisting of a resistor, an inductor, and a capacitor connect a series or in parallel. The RCL part of the main is due to those later being the use electrical symbol for resistance, inductor, and capacitance, representative the circuit from harmonic circuit for current and we resonate a similar whereas a RLC circuit will. The main difference that present of the resistor make is that any isolation induction in the circuit will get away over time. This is not keep going by a source. The effect to resistance is called damping. The presence of resistance and also reduce the peak resonance frequency somewhat. Some resistance unavailable in real circuit, even of resistor is not specification in that as a component and dear to LC current as the propose the theory. The many application use the circuit. They are used in many different type or circuit. Any important application is for tuning, such as in radio receiver or television set, where they are used to select narrow range of frequency from ambient radio wave. In this role, the circuit often called a tune circuit and RCL circuit can be used a low band pass filter, band stop filter, a low pass filter, or high pass filter. RCL filter is referred as a second order circuit, meaning that any voltage or current in this row circuit to offer called a tune circuit, and RCL circuit can be used as a band filter, a band stop filter, a low pass filter, or higher pass filter. The RCL filter is disabled as a second order circuit, meaning that any voltage or current in the circuit can be resolved by a second order different equation, the circuit analysis.
Hello, Sama Sejahtera and good day. So my name is Chia Chin Yong from BEI Group Melaka 1. So I will take part for the procedure and the calculation for our circuit. So we proceed for it. So the procedure for designing a passive low pass RLC filter circuit in more detail. So we have to determine the specification, define the cutoff frequency FC and the desired attenuation in the stop band. This parameter will guide the design process, select the configuration, choose whether you want to use the RLC filter or parallel RLC filter based on your circuit requirement. Calculate the component values, calculate the values of resistor and the reactive element L or C. Based on the desired cutoff frequency, the component value depend on the cutoff frequency and the desired impedance. Use the appropriate formula for the chosen configuration. So for the series RLC, this is the formula that has to use. If for parallel RLC circuit, that will be different a bit with the series RLC. Okay, so design the circuits. Once you have to calculate the component value, construct the RLC filter circuit using the chosen configuration. Ensure the RLC resistor, inductor, and the capacitor are connected in the correct order. So we continue. So this is our circuit given. So you can clearly see the voltage voltage source connect with the inductor, resistor, and the capacitor. So we can solve it. So this is a V in, this is a V out. So since we didn't have the value, so we assign the resistor in 2K, inductor in 2 Henry, and the capacitor in 2 microfarad. So we have to derive the transfer function hash omega and explain the type of transfer function, voltage gain or current gain or transfer impedance or the transfer admittance. So since the transfer function is this one, hash S equal to VO over V in, so S equal to J omega. But since we have some changes here, so you can see the R equal R over 1 plus SRC. So we have to substitute the HS into this one. R over S square RLC plus SL plus R. So or finally you become this one the transfer function R over negative omega square RLC plus J omega L plus R. So because the H0 equal to 1 and the H infinity equal to 0, so we can conclude that from the table 14.5 that the circuit in this figure, so here is a second low pass filter. So the magnitude of the HS is 1. So we can clearly see this is the formula for it. Slide. So we can see this is the corner frequency is the same as the half power frequency. So that is where H is reduced by a factor of 1 over V square, because the value of HW is 1 and the corner frequency, so E equivalent become after squaring. So this is a formula after we simplify. So we become 2 equal to bracket 1 minus omega C square LC square plus omega C L over R square. So by substitute the value of RLC inside the value inside the formula, so we can get this one formula. So assuming the omega C is in K radians per S, so this is our result that we get. So we can got 2. So solving the quadratic equation is omega C square, then we can get the omega square also equal to 0.5509 and negative 0.0034. Because it's real, so this is our omega C equal to 0.72 KRAD. Next, so we will calculate how to find the poles and zero. So first, given the value is previously resistor equal to 2 kilo ohm, L equal to 2 Henry, capacitor is equal to 2 microfarad. So that we can calculate the poles and zero. As well, we can calculate together the center frequency and the bandwidth of cutoff frequency on the filter. So first, for the poles and zero, so we have the transfer function for the second order RLC low-pass filter is HS equal to 1 over S square plus RLS plus 1 over LC. So we can just plug in the value. So this is our after substitute. So we can simplify. So this is our result. So by solving the quadratic, S square plus 1000, so plus also 250,000 equal to 0. So we can find the value of the poles. So for the center frequency, so since the formula for the center frequency FC is FC equal to 1 over 2 pi square root LC. So also same, we just plug in the value. So our center frequency after the calculation, our center frequency that we get approximately 79.577 Hz. So for the bandwidth of, we call it cutoff frequency. So this is a formula. Bandwidth equal to 1 per 2 pi RC. So same, we just plug in the value. So we have, after the calculation, we can get the approximately 39.79 kHz. Therefore, the poles and transfer function need to be solved from the quadratic equation, and the center frequency is approximately 79.77 Hz, while the bandwidth of the cutoff frequency is approximately 39.79 kHz. Okay, so continue the poles. To find the value for the poles, we need to solve the quadratic equation of step from the transfer function. So just now this is the the quadratic equation that we found. So this is a quadratic formula. S equal to negative b plus or minus square root b squared minus 4ac over 2a. So for the given value, so this is our given value. So we just use the value and plug in this formula. So we get this formula in this. So simplify. After the simplify this one equation, so we get this one. S equal to negative 1 kilo ohm or S plus minus square root 0 over 2. So this is a discriminant. The formula is equal to 0. So both the solution S will be the same. So S equal to negative 1000 ohm over S over 2. So after simplify, so we can get the poles are the negative 500 ohms per S. So this is all my part for the procedure and the calculation for the circuit. So for the simulation that I pass to my next team member. So thank you for it.
Assalamualaikum warahmatullahi wabarakatuh. Thank you, Mr. Chia, for your brief explanation. My name is Muhammad Amirul Amin Mirazali. I will take this presentation for simulation and analysis process. Ladies and gentlemen, today I'm excited to present to you a demonstration of RLC filter circuit using multi-sim software. These power tools allow us to design and simulate electronic circuit with ease. So let's dive right in and explore steps involved in creating and analyzing an RLC filter circuit. First thing, we need to launch our multisim in our computer. Once the software is open, we can proceed to create a new project. To do this, we select the new project from the file menu and specify a name, location for our project. Now let's add the necessary component to our circuit. In the component panel, we search for and select resistor, inductor, and capacitor component. We can simply drag and drop this component into our workspace. Next, we need to configure the value for our component. Double-click at each component and open its property dialog box and enter the calculated value obtained for our previous calculation. This step ensures that our circuit matches the desired specification. With the component in place, it's time to connect them appropriately. We using the wiring tool provided by Multisim to establish the connection. Start by connecting the input signal to the resistor and proceed to connect the resistor to either the inductor or the capacitor, depending on whether we want a series or parallel configuration. To generate an input signal, we search for a voltage or current source in the component panel and drag and drop into the workspace, connecting the circuit to input of resistor once again. We configure an input signal by double-clicking on the source, setting parameters like frequency, amplitude, and waveform. To measure the output of our filter, we add an oscilloscope or voltmeter from the components panel. Drag and drop the measurement onto our workspace and connect to output the filter circuit. This allows us to observe and analyze the output before we run the simulation. It's important to configure the simulation setting. Click on the simulation menu and select analysis option or simulation setting. Here we can set the desired simulation times, tolerance, and other relevant parameters. Once the simulation completes, we can analyze the output of waveform using multisim built-in analysis tools. These tools provide valuable insight into the circuit behavior, such as frequency response, cutoff frequency, and other parameters based on our analysis requirement. Our circuit will consist of a 2 kilo ohm resistor and a 2 Henry inductor capacitor with 2 microamp, function generator, oscilloscope, and board plotter. Once the components are in the place, we will take the configuration value. and enter the specified value for resistors such as 2 kilo ohm and inductor 2 Henry and capacitor as 2 microfarad. This step ensures that our circuit accurately reflects the desired component parameter. To measure the output response for our RLC filter circuit, we add oscilloscope and its component. Additionally, we will employ the Bode plotter component in multi-system to analyze the frequency response to our RLC filter circuit. This tool will provide valuable insight into the circuit behavior across the range of the frequency. We can set the parameters such as simulated time, tolerant, and other relevant options. This setting ensures accurate and reliable simulation result. After the simulation complete, we can analyze the output waveform using oscilloscope and study the frequency response characteristic using a Bode plotter. This tool within multisim will help us understand key parameters such as gain, phase shift, and current of frequency, enabling us to evaluate the performance of our RLC filter circuit accurately. Finally, the utilization of multisim along with the component empower us to simulate and analyze the behavior of RLC circuit filter effectively. We can visualize the circuit response, gain insight into the frequency characteristic, and evaluate the performance before physical implementation. Thank you for your attention, and I hope the simulation demonstration using multisim has been provide you with valuable insight into the capability of this powerful circuit design and analysis tool. So I pass to the result part to my team member. Thank you very much.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you to my teammates, Mr. Muhammad Amirul Amin, for your explanation, the simulation part. My name is Muhammad Shafi Irfan Beruslan. I will continue the explanation for the result after doing the simulation test using the multisim. Okay, here I will explain to you the result after we doing a simulation test using oscilloscope meter in multisim. From the figure, as we can see here is the oscilloscope result Vout, which is for the 100 Hz equal to negative 1.568 volt, and for the 200 Hz we get 272.302 millivolt. For the 400 Hz we get 20.627 millivolt, and for the 800 Hz we get 12.429 millivolt. Also, we can see at the figure a different frequency, which also with a different waveform. Okay, here is for the result for the center frequency simulation test by using Bode plotter meter. From the calculation, we get 79.577 Hz, and from the graph at the height line result, we get 78.242 Hz. And for the bandwidth, or we call cutoff frequency, from the calculation we get 39.79 kHz, and for the graph at the cutoff line result we get 39.66 kHz. Okay, next for the discussion. The RLC low-pass filter displays the negligible attenuation at the frequencies below the cutoff frequency, enabling the input signal to pass through with little or no use distortion. As the frequency exceeds to cutoff frequency, the filter attenuates the signals, lowering its loudness. The order of the filter determines the rate of attenuation, with higher order filters producing steeper roll-off slopes. Passive RLC low-pass filters are used in a variety of electrical and communication systems. Also, they are frequently used to reduce high-frequency noise from audio signals. that to extract baseband signal in communication systems and to function as anti-aliasing filter in analog to digital conversion operation. It is critical to understand that passive RLC low-pass filters have their own limits. Also, they introduce signal root losses which can have an impact on overall system performance. Furthermore, they may exhibit phase change in the basebands, affecting the phase accuracy of the filtered signal. A passive RLC low-pass filter is a fundamental electrical component that is used to reduce higher frequency signals while allowing the lower frequency signal to pass through. Its performance is determined by the component value and cutoff frequency, and it is used in a variety of electrical and communication applications. And finally, for the conclusion, in the end of the simulation, a passive RLC low-pass filter is an electrical circuit made up of resistor, inductor, and capacitor that are designed to attenuate higher frequency signal while allowing a lower frequency signal to pass through. Its main purpose is to remove high frequency noise or undesirable signal from the desired input streams. The resistance, inductors, and capacitors level used in a passive RLC low-pass filter determine its performance. The cutoff frequency, also known as the -3 dB frequencies, and it is an important parameter that defines when the filter starts attenuating the signal. So that's all for my parts. Thank you very much.